Alright, so I'm going to go through the chemical reaction of this part. So we're talking about, now safety goggles and gloves on. The other two experiments work essentially the same way as you saw in the other two videos, but this one I want to show you personally. So the reason I'm using gloves is because that this is a hydrogen peroxide is roughly a 30% concentration. So one of the things we talked about is things that change reaction rates is the concentration. So like we talked about in my class the like pool chlorine. There's a small amount of drinking water, very small amount, trace amount. But there's more in a pool. You've probably been to a pool where there's your eyes get bothered because of the concentration of the chlorine. So this is kind of the same thing. This is hydrogen peroxide. This is going to be what we're going to be breaking down. Now you'll notice that the hydrogen peroxide is in a brown bottle. The reason it's in a brown bottle is because as soon as it's exposed to light, the energy from the light, even in the smallest amount, starts to break it down into its component parts of hydrogen and oxygen, being this H2O2. Now in my graduated cylinder right now, I do have, if you can see in there really closely, just a little bit of dishwashing soap. It's just regular generic dishwashing soap. Nothing that's causing anything reaction. There's no real formula for dish soap because it is a combination of different elements. So if you look at it's a mixture per se. All right, now that was interesting. We need 20 milliliters of the hydrogen peroxide. Again, this is 30%. So the stuff you have at home or you buy at a grocery store or a drugstore would be about 3%. You can actually, I think on the bottle, quote me on this, it's for cleaning out cuts and disinfectant. Now this, you can notice I'm wearing gloves and I'm the most safety conscious. I wear gloves when I'm using this 30% concentrate because it does create, it is much higher concentrated as we're talking about. And that higher concentration will actually burn my skin if I'm not careful about it. So we have our as you can see through the slit, we have our hydrogen peroxide, we have our dishwashing soap. Now, they're not really mixing right now. As you can actually see, the densities are kind of separating them. The soap is designed to catch the gas that's given off as this is breaking down. Now, as I said, even this light, that hydrogen peroxide is breaking down into hydrogen and oxygen. It's just happening at a very slow rate. One of the things that we can do to increase the rate of a reaction is to add what's called a catalyst. And a catalyst is just any chemical. Now, the catalyst itself is not used up in the reaction. What it does is just helps to facilitate the reaction. Basically, a bunch of molecules saying, hey, come on, let's go. Because right now, as I'm talking, the hydrogen peroxide, H2O2, is breaking down to H2O and water vapor and oxygen gas. So, here is the catalyst, sodium iodide. So what this is going to do is once it connects with the hydrogen peroxide, it's going to start breaking those molecules apart much quicker. You'll see a greater release of gas. You'll also see thermal energy change. Now, right now, my substance or a mixture, it's a mixture, I apologize, is about 21 degrees Celsius, about room temperature. Is what you'd expect because it's in my room. Now, as I add the last ingredient, we're going to see the reaction. Again, what are some signs of a reaction? Production of a gas, change of temperature, change of color. Now, if I wanted to, I could add a color, but this is being a demonstration when I just want to do this generic. Change of temperature, creation of gas, formation of bubbles, which this was going to be. And then what the bubbles are is the dishwashing liquid catching the material given off. So here is the reaction. This is called foamy, or also known as elephant toothpaste. And we see a tremendous creation of gas. We're at 55, 59, 60, 65, 70, 72, 73, 73 degrees Celsius. Really hot. Now, that's shiny chemical reactions occurring. Now, this is what's happening is you can see the water vapor breaking off as water vapor. That's the water part. But the gas given off is oxygen. And as we discussed, oxygen is necessary to burn. So if I bring it close to the reaction, there's enough oxygen to cause that. Remember, oxygen is necessary for any flame. So if I kept it there, the oxygen would continue to fuel it. So again, this is a decomposition reaction. What we've basically done is we have taken a hydrogen peroxide, H2O2, and we've broken it down into its component parts of water vapor, H2O, and oxygen, just molecules of O2. There's a video that follows this that might help to explain, but hopefully you enjoy that reaction.